How do you normalize quantum states with Dirac notation? Imagine trying to make sure every piece of a puzzle fits perfectly so the picture makes sense. In quantum mechanics, this is what normalization does for quantum states. It makes sure the total probability adds up to 1, so everything lines up correctly. In quantum mechanics, we use Dirac notation to describe states. A state is written as a ket, which looks like this, psi. Its dual, called a bra, is written as psi. When we take the inner product of a bra and a ket, written as psi phi, it gives a complex number called a probability amplitude. This number tells us how likely it is to change from one state to another. Now, for a state to be valid, it must be normalized. That means when we take the inner product of the state with itself, psi psi, the result should be exactly 1. This ensures the total probability of all possible outcomes is 1, which makes sense because probabilities can't be more than 100%. To normalize a state, first find its norm. The norm is the square root of psi psi. Think of it like measuring the length of a vector. Once you have this number, divide the entire state psi by it. This gives you a new state, written as psi, divided by the square root of psi psi. This new state is now normalized. Let's say your state is a combination of two basis states, written as psi equals a times 0 plus b times 1. To normalize it, you first calculate psi psi. This equals a star times a plus b star times b, where a star and b star are the complex conjugates of a and. The sum gives you the total magnitude squared of the state. Then, divide the entire state by the square root of this sum. That's your normalized state. Normalization is really important in quantum computing and quantum information. It makes sure the probabilities stay consistent and the quantum system behaves correctly. Without normalization, calculations could give probabilities that don't add up to 1, which would be physically impossible. So, by understanding how to normalize states using Dirac notation, you're making sure your quantum states are valid and ready for use in real quantum systems. It's a simple but essential step that keeps everything mathematically and physically correct.